Hey guys, welcome back to another MBB control systems video, and today we're going to be looking at TATU 2015 and we're going to be looking at the root locus diagrams. We're looking at question 1, TATU 2015, and the question goes as follows. So they tell us a control system has a block diagram of the form shown in figure 1. So we have a block diagram that looks like this. So we see we have our controller function there, transfer function, we have our plant function, and then this is our plant function. So it's like this, it's there, and then they tell us that so they say, as indicated, the specification calls for the step response to comply to the following: a maximum overshoot of 5%. We need to write this criteria down. So they tell us that the percentage overshoot must be maximum 5%, so it must be below or equals to 5%. A plus minus 2% settling time of less than 5 seconds, time of less than 0.5 seconds. So this is a plus minus 2% band. So what that is, as a reminder, if we have a graph and we have this, our settling time, so this is our response. Our settling time will be the last value that lies inside these lines. Our response is y over t. And then our settling time will be the last value, which is there, and then our settling time will be ts. So it's that value there. So yeah, in the plus minus 2% band. And yeah, so that's the criteria they give us. And they also say the smallest possible steady state error. The smallest possible steady state error as well. Smallest possible steady state error. Smallest steady state error. Right. So yeah, so let's get into the question. And they say use the root locus diagram of the system and determine the gain to be used as controller GC equals to K to ensure that the system meets the specification. So we basically have to find the value of K such that our system response meets that criteria there. So this must basically, our settling time must be below 0.5, and then our percentage overshoot must be below or equals to 5%. Right? So let's use Python to see how we're going to do this, and how we're going to design a controller that meets this criteria. So how are we going to design a controller that ultimately meets our criteria? So then what we do is we go to our Python code. There's our Python code here, and then I'll put the Python code there. And then a lot of things are open. This. I want the Python code. So I have my Python code now, and it's really small. Okay. So this is our Python code there, and basically what we want to do is we want to find the value of K, for which is going the K value. So this is K. So basically our control system looks like this. So let's just draw the control system. So our control system is as follows. So we have R, that there, we have K now for our controller, and we need to determine the value of K that's going to give us our response. That's Y. Then we're obviously going to feed that back, so it's the unit feedback, and that's negative, and that's positive. Okay, so then what we're going to do is we want to determine the value of K. So that's actually just so we don't get confused with letters. This is YS. KYS. Then we also have RS. And then, so what we're going to do is we're going to determine the value for K, which is going to give us our response. So then we go to our, we go to Python. So we go to Python. And then what we're going to do is we're going to go to an example code. So if you ever forget which code is which, you can always go to your formula sheet and then scroll to the bottom. If we scroll to the bottom, we'll see that they give us codes. They give us all the different example codes. So they say root locus diagram method of PID, R locus. So there's also all of these ones, but what I recommend you do is you just go straight to, you look for, you download the examples or chapter 7 code and you go to .dot example 7.7. So we do that and we will find, so we do that and we'll see we have a code that looks like this. So this is our code here. And then what we're going to do is we're going to copy it first, paste it in there, we run it all. No problem. You just have to make sure, you might get an error, just make sure that this is imported. It's very important that this code is imported, that you have this saved in the same place as the thing that you've opened. So we do that. And then what we're going to do is, okay, so we need to open up here. So then what we want to do is we want to determine the value K. And so the first thing we're going to do is we're going to determine our, so we have G. So the first thing we need to do is we need to determine G. So we're going to write down G. So, and you can literally just copy, if you look at example 7, when 7, you just, in all of this, and you just want to get G first. So we copy G. And we paste it in there, and we want to define what G looks like. So all of this over here, this poly1D, is it just defines our subcomponents. So it defines, because obviously multiplying all of this out would be, so this is G, and I'm multiplying this out by hand, adding it would be a bit tedious. So what we can do is we can use Python. So you create the first one as a polynomial, so it'll be 1 and 8. That will then be 1 and 18. Will be 123, and then all we do is we just multiply them out. So poly1D converts this into a polynomial. So if I say print, if we just look what that looks like, you see we're going to get something that looks like this, right? So this is well, the first one there, 1x8. That's this one there. I can just, that's so 1x8. So it's this one, right? So we see we are 1x8. So it's pretty much, that's what that looks like. And then, so we do that for each factor. We multiply them out, and then that's going to give us something that looks like this. It's going to give us this. Oh, wait, no, we want it to be, give us that. So this is that's the bottom that's multiplied out. And then we obviously then just, so then we extract, so we extract the coefficients of C. So when we do that, we're going to get this. Over there, so we extract, so when we say gn.c, we're going to extract, so let me actually, wait, I see I put that in the wrong place. So if I run this, and now we run that, we see this is what it looks like, this gden multiplied out, we get that, and then we're going to extract c, and then we'll see we get an array out, and then that's it. So this is just a way to do it. If you want to extract the components as an array, and then we just plug the gnum in there, which in our case is actually 40, and then we have the numerator, which we just calculated, which is that there. So then I can do this, and then we can G. Okay, get rid of this, so we got the wrong one. That, and then if we run G, we'll see we're gonna get that, right? So then what we do is we just go to our code,